But with that, today, welcome to Model Development Production. Our case study, we're going to be focused on part 2 today. All right, so our goals for this session. We're going to use Jupyter and we're going to explore the Penguins Seaborn data set. So we'll get again from Seaborn. The reason I like sticking with Seaborn is just because it's one of those places where you can always get that data from. So you can try different things on it. We're going to clean it. We're going to create some visualization. So similar to how we did yesterday. So the goal of this weekend was for you guys to get fluent at creating these visualizations. So you're starting to see the pieces to them and how they go together. We're going to go ahead and do that splitting again. So we'll use that formalized method we learned yesterday. We'll train and test. So we'll use another code block here to evaluate which model is better or which model is performing better. And then we'll get into that optimization piece. So we'll look at the ways to optimize our model as well as to kind of see that classification report. All right, so let's go ahead and get started. I'm gonna go ahead and put our imports in first. So those are the imports we'll be needing today. So hopefully these first 5 up here look pretty common, especially the first 4 we've used this a ton. Stats Models API is something we occasionally use. I like to have it in there in case I always think of like some nifty little connection we can make with it. Here we have a standard scalar. So what that's going to do is help us standardize data if we choose to. We should know what train test split is. We used that yesterday. Multinomial naive Bayes is a classification tool. Logistic regression, oddly enough, kind of works with both. We've seen that in both classification and regression. Our classifier, so K-neighbors classifier, random forest classifier. These 2 are pretty cool. Our classification report and our confusion matrix, we'll see those today. And cross-fail score, we've already seen that, as well as grid search. So hopefully you're starting to get comfortable with what each of these imports are. Something I would suggest and something I keep myself is when I'm first getting used to what these different libraries do, I kind of keep like a separate file of every import I use and then a brief description, like a comment of what it's for. Especially when you do these, like the general imports, like, okay, like we get that. But when you use one of these, like from this, import this, that's something I would comment out personally until you kind of have like a really firm idea of when you need it and why. Because a lot of times you'll work through tutorials or you'll complete a project and then you'll forget exactly what the purpose of one of those things may have been. All right. So first thing we're going to do is we're going to go ahead and bring in our data frame. So we're going to call it df penguins. And then we'll go with sns.load dataset. And it is penguins. Okay, so hopefully we kind of got this pattern down now. So I'm trying to show you. So that's the kind of exploration we want to see. So the typical way we want to do this is we're exploring the data. So I'm going to go ahead and say dfpenguins.info. That's the one I always want to start with, just to kind of see what we have in there. So we have the non-null data type here. If we're looking, so we see the number of non-nulls. So here we have 344, 344, 342. Now, again, if we read through this, we can see our range index is the first thing that comes out with .info. So this is always one of the first ones I suggest we just use to kind of take a look at things. So there's 344 entries. It tells us 0 to 343. So what that means is it just the first row is row 0. So just like kind of how we talked about the 0 indexing kind of inherent in Python. And it says we have a total of 7 columns. So notice the column numbers 0 through 6. So again, that's 0 indexing. So if I have 344, we can look here. If I'm counting my nulls here, if I have 344, there's going to be only 342 here. So there may be a handful of null entries here, actually, if we're looking down. And then for sex, we only have 333. So we can kind of see there again, what depending on what we want to predict, we may have a few. So we also have our D types here, we have our objects, and then we have our floats there, those 4. So what this data set is working with is we have the species in the island. So the species of a penguin, the island that they were living on, and then the sex of the penguin. And then here are our descriptors, so our different measurements here. So if you've done anything with the iris data set, this is kind of similar, but it gives us a little more variety of what we can select from. So let's go ahead here, and I'm just going to go do the df head. So I'm going to say df penguins.head, and maybe let's just check out the first like 10 rows of this. So we can see here, we do have just an example on row 3 here, as well as a few down here that we can see, where we do have some of those NaN, those NaN values. So that means we have a null value there. So the way we can tell that from this table is if these numbers are not all this number. So since this is 344, since some of these are not 344, namely the sex variable there, it seems like that one's the one that's missing the most. However, there's a couple with like blanks in there as well. So we can see that there. Another thing we can typically do here is look at where we are going to go ahead and say our describe method at. So we could say dfpenguins.describe, and we can get some summaries there. So if we look at these variables, these are all pretty good for predictions. Bill length here, here's our mean, our standard deviations, again, a large scale factor, smaller. Same thing here with bill depth, flipper length, and then the body mass is probably the closest, but I mean, it's still over, it's about a little more than a 5 times multiple from standard deviation to mean. So again, that's something that you'll notice that the more you work with, the larger that multiplier is to go from standard deviation to mean, the kind of easier it is to predict within your data, just because the numbers aren't as spread out. All right, so let's see what we want to get here. Okay, we get this, good. All right, so let's go ahead and look here a little more at description here. So what we want to do is look at how we can remove some of these variables. So let's say we want to get rid of stuff that has our nans in here, so that it does not have that. What I want you to do is go ahead and think here how we can get rid of that to avoid some weird stuff in our visualizations. So I want you to think of any type of ways you've removed variables that show up as NaN or nan. So if we're looking here, looking at which one shows up the most, what would we want to start with removing? So which one is showing us the most null variables here? If we're looking, we see the variable sex that has the lowest number of non-null columns. So if we remove that, that might get rid of some of these others. So I had one up here, this row 3 had a lot of nans. Typically you want to get rid of those if you can. You don't need to, I guess you could say, but it's one of those things like when we work with data, we want data as complete as possible. So one way of doing that is going to be ahead and using this type of command. So I'm going to go ahead and throw this in the collab file as well. So in this case, we have the sex missing for the penguins. Since we already have a fairly large data set, we have over 300 entries, we can go ahead and remove these. And this is just going to avoid those like odd visualizations, kind of how yesterday we visualized and then we tried to clean it up. In this case, we're going to go ahead and just remove some of those first. So here, I'm just going to rename it dfpeng. And this is just so I don't do it in place kind of cleaning. You could do dfpenguins again. However, again, when we clean a data set, I always try to do it in like a version control thing. So maybe you want to do dfpenguins1 or whatever you want to rename this as. I'm just gonna go dfpenguins1. That seems like a pretty nifty way to do it, right? So that numeric idea of version control. So I started with dfpenguins. Hey, I'm cleaning, I'm changing it. I'm gonna rename it as 1. That way, if something goes wrong, I don't have to go through running my imports again. And the reason I suggest doing it that way is because, the longer you are in a project, if you change something and you mess it up, you literally have to go all the way back up to here to rerun it again. So when you're doing your initial exploration, embed some type of version control in there when working with data sets. So what we're gonna do, this is gonna be equal to dfpenguins. And then I'm gonna go ahead and say what I wanna get rid of. So I'm gonna say dfpenguins, and I'm gonna say the variable of sex, and then what I want is not null. So dot not null, with our parentheses there. So I'm gonna go ahead and comment this out as well. So what that did, if I look at my shapes here, right? So if I say dfpenguins.shape, or if I say dfpenguins1.shape, we can see there we removed all of those rows. So this number 333, it matches with what we had up here, right? The number of non-null rows. So this is kind of one of those ways whenever you have multiple columns there, you can sort of see like, okay, like how many of these are going to be those null values? If we want to explore a little more, we can go ahead and say dfpenguins1.info, and let's see if we have any of those issues now. An initial check here, we should be good, right? We all have the exact same amount that are non-null. So by removing those null sexes, everything else was kind of fixed in there. So all of those are now good. So whatever you have a full match here in this column, these are all the same number. That means you're good. everything now no longer has nulls. Now, you'll see a lot of different ways that people work with missing data. So that's kind of its own like entity there. Some ways that people work with missing data is if your data is large enough, you can just remove them. Other ways you can do it is you can replace with like a columnar mean. So for example, maybe I wanted to replace here. Let's say I was missing some in body mass. Maybe I just took the average of the column. Or maybe I took the average with respect to sex and then replaced those in there. So there's other ways you can do it. However, if your data set's really large, you can always kind of just like, if they're missing values, like whatever, we don't need them type thing. That's generally an acceptable way of working through. All right, so let's go ahead here and dig right into a visualization. Oh, awesome. Okay, so great question here in the chat. Let's go and talk about that. So in this case, a kind of hard and fast rule, there isn't really going to be a great rule for when we can remove it versus when we want to impute that or like kind of take an average for those missing values. So I can say this here. If I'm missing a column value, so let me go ahead back here real quick and let's look at this one here because this is a great question. So for here, if I'm missing this value here of sex, so I'm only missing this, I have all the other information. Now, let's say I'm not using sex at all in my analysis. I can just drop this column and I don't really care then if that's missing. So we don't necessarily have to remove everything if we're not going to use the value that's missing. So if I'm not concerned about sex, if I'm just looking at penguins in general, then I really don't care if this isn't here because I could say, you know what, like I'm not going to use it anyway, doesn't make a difference. Now, let's say I was looking at body mass. So in this case, I could go ahead and say, hey, maybe I'll impute this value here. So maybe I'll take the mean of the column and put it in here. That's not going to change the distribution a ton if we just use the mean of the column. But again, it's one of those dependency things. Like if I'm worried about male or female here, then maybe I want to replace that with, again, if it was male and I was missing one, then maybe I'd replace it with the male average. So what I would suggest with this is when you're going to go through these values, think about all the dependencies. So like if I'm predicting sex, then it's a big deal if I switch these values. However, if I'm not predicting sex, then I can maybe impute some of these values based on it. So it kind of comes down to like what is going to be. So I will say this, the problem when we impute too many values is that then we kind of overly generalize, I guess you could say, or generalize our system, our model. Because if we just keep taking the average, like if you think about a data set, so if I have the data set here, let me just go ahead and type it in the chat. Or same thing with like the median, if you just keep imputing that in there, you kind of like raise the peak. So you artificially increase the peak in there. So like if I had the data set 1, 2, and then 3, and let's say I wanted to impute a value there. So I was missing something. I said, okay, well, I'm just going to impute the value with the median. That would give me 1, 2, 2, 3. If I'm missing another value, all of a sudden I'm imputing another median. So what it's doing is it took what was initially a uniform distribution and it's kind of normalizing it. It's forcing that peak to raise in the center. So when it's working with mean or medians there, oftentimes we just kind of see that center rise the more that we impute values. So anytime I put data in, I always want to make sure that it's not a large percentage. So like if I'm looking at a data set and I have, like in this case, what do we have? It was like, let's see what percentage of our nulls we had. So we had, was it 344? So it was only about 3% of our data that was null. So we could scrape that and it's not a big deal. So I took the number that I was keeping. So the total minus that, just see how much it was. So it's 11. So 11 out of 344, we're at less than 3% that we're scraping off there. So it's not going to make a huge difference. However, if we, just replace them, that really wouldn't matter because it's only 3 values. Like it's not gonna make a huge difference. But in this case, it's like the more you kind of put those imputed or calculated values in, if you're just taking like a general measure with no specificity, like I said, if we had the sex variable, maybe I could replace it with the average of that penguin sex or the average of that penguin sex on that island. But if you just kind of take a general mean or median to replace with, what that often does is kind of artificially inflate your middle. So if you can, a rule of thumb is if you can, lose 5%, maybe 10% of data, depending on how big the data set is, if you just scrape the non-exist, like the missing ones, it usually does a better job of modeling. So what we're gonna do here is we're gonna visualize our quantitative variables first. So what I want each of you to do is I want you to try to create the visualization here for our 4 quantitative variables. So our 4 quantitatives are these 4 here. So I want you to try to make a histogram for each of them. So just like we did yesterday, kind of that combined plot, I want you to go ahead and try and make that histogram. I'm gonna go ahead and put together ours as well. So if you want to use Seaborn, like again, I just like to set the color codes up first, just so that way I can kind of pull those palettes in. This is also a great thing to have in here if you ever use like the dark mode in anything. So sometimes I use like a dark mode on my browser by using this. It kind of cleans that up a bit. And I'm just going to use that bright one. For this part here, our fig and axis, we can go ahead and say plt.subplots. And then since we only have 4 variables here, so 1, 2, 3, 4, probably the easiest is just doing the 2 by 2. And then when you're getting used to fig size, so I will say this is really dependent on the size of your screen or monitor. So this argument here, it has defaults. It kind of figures out, based on the dimensions of your device, like what to use. I always say like play around with it and kind of get the idea of what shape you want. So like here I have 4 plots, so I would like a square. So I made these dimensions the same. However, if you run it this way, you can kind of adjust it however much you'd like to get to the visual that you find most useful. Those spaces don't matter. I just personal preference kind of thing there. And then if we're using a histogram, we want hist plot. Just going to kind of leave that blank for now. Color equals colors, whatever we want in there. And AX equals axis, whatever we want in there. So just as a reminder here, I'm gonna go ahead and throw a quick visual up here. So when we are creating these figure axis subplots, what we want to think about is our labeling. So I have 2 rows by 2 columns. So that means my first one here is 0, 0 in brackets. Here, if I go to the right, so it's row 0, column 1. And then this would be row 1, column 0. And then 1, 1 there. So row 1, column 1. So again, the rows in columns are indexed at 0. So this would kind of be our visual of where our plots are going to be. And since we're doing that 10 by 10 dimension, it should look, something along these lines. So pretty square. So again, kind of visualizing, getting used to what those subplots mean. So since we know we're doing 4, like I said, kind of shorthand way here is to copy and paste this. And then my variable names here. So I like to use that columns argument there to get those directly. So I'm going to say df penguins 1 dot columns. So what we want here, I'm just going to go in order of where they are. So I'm going to go ahead and let's say bill length, depth, the flipper length, and then their body mass. Colors here. So I just go in order. I start with 0, 1, 2, 3. And you can play around with those, kind of choose which ones may stand out the most or which ones you like the best. And then for our plots, so we already showed those. I'm going to go ahead and use 0, 0, 0, 1, 1, 0, and 1, 1. Last thing, we want to go ahead and get our title in there. So you notice I'm doing a little less commenting out on these today. So now it's more so focusing on what we can tell from it. Then again, for this one here, that y is equal to 1.01. If you want to see the difference using it without that part, that it defaults to 1, meaning like right on top. That 0.01 just gives a little bit of white space in there, so we make sure it's not covering up anything. So when we get that visualization, go ahead and zoom out a bit. Here is what we're looking for. So something looks really skewed. Awesome. Yep. So awesome. Notice there in the chat, if you guys check it out, body mass in grams there is looking rightly skewed. So yep, we have that nice, it's got that peak to the left. So if we kind of think about the center of our data spread here, so from min to max, if we're looking, we do have that peak over here and then kind of a gradual decline on that side. Same thing over here, if we look at that flipper length, right? We kind of see that same skew. Not as nicely shaped here as the body mass, and we have this one little kind of missing thing. Apparently there was, not many penguins with this length, but again, we kind of see that same general shape. I'd say bill length is, relatively normal. So the millimeters here, we can kind of see this is a relatively normal distribution. Over here, bill depth, maybe a little left skew, so maybe the median is going to kind of drag it up a bit. But yeah, this would be a great example here if you're looking for something that we'd say is going to be the skew there. So it's skewed to the right, rightly skewed. This is a great example here. So positive side is something we're seeing now, the difference between today and yesterday is yesterday we put 7 plots together on an 8-piece grid. If you're going to be presenting stuff, now again, if you're like just the one looking at it, like if you're doing your own research, cool. Like you put 50 plots on one grid, it's whatever you're comfortable with doing. However, if you want to investigate something specifically, using less plots gives you a much better visual. So you can see here, we have a much clearer visualization of these graphs than we did with yesterday's. So yesterday's, it was kind of like, I had to like zoom in a bit, zoom out. So here, it's one of those less is more type things. So even if I had, 10 different variables, maybe I would do a couple plots here, like do, groups of 2, groups of 5, whatever it may be. So the idea that when you do less, you often get a clearer picture, and it's also easier, like, kind of snip tool thing if you're putting it into a document or a presentation somewhere. Something I would look at too. So the idea of left or right skew. So let me go ahead and bring up something. Where are we at? Let me go ahead and pull up. Honestly, just Googling a picture real quick here, just because there's a really good one I usually use that shows up on Google. Where are we? Okay, so when we're looking at our kind of common distributions here, there's another one that we would call bimodal. So bimodal is when it has kind of 2 peaks that are equally heighted, I guess you could say, or roughly equal height. However, what this really gets down to is when we're going to go ahead and say, what's our best measure of center? So a normal distribution, again, we kind of have that hill shape. It may not look perfect on both sides. Uniform distribution means like everything is occurring roughly equal. So if I were looking at a uniform distribution, it would basically mean that like no height is more common than others. A skewed left distribution means that the height of the data is mostly on the right. So if I draw a line down the middle of my data, and when I say the middle, I just mean in terms of like I guess you could say the spread here, how far apart it is. So if I look at my data here, this is my smallest value, this is my largest. So if I'm looking at going to say, hey, like what's the middle? It would just be in the middle of the data available. So this would be the middle of my data. So since in this case, most of my data is to the right of the middle, we say it's skewed to the left. So skewed is one of those like weird words where I always tell students think of opposite. So if most of the data is on the right, we're going to say it's skewed left. Or over here, if I draw it down the middle, most of my data is on the left, so it's skewed to the right. So when we have one of these types of distributions here, and I will say these 3 are the most common. There's not a whole lot that oddly enough comes out as uniform. So it's kind of its own category of data we work with. However, for these 3 here, so if you have approximately normal or normal data, we say the mean is the best measure of center because the mean, median, and mode are all roughly equal. However, if we have one of these here, if we have skewed data, then if I'm looking for the best measure of center, I'm looking for the most representative measure of center, I would then want to use the median for that. Because if we look here, the medians would be, just by counting the frequencies, the medians would be kind of pulled over and give you a better idea of where that data is at, whereas the mean is going to be more influenced by these high and low extreme values. So the mean of this data is probably going to be somewhere around here, and that's not going to tell me as much about where the true center of my data is the median would. Whereas in the normal distribution, it's always kind of in the middle, so we can use them there. On understanding skew in data. All right, so if we want to go ahead and check out our box plots now, let's see if we have any outliers. So all we need to do with this is I'm going to do the Control A, Control C to copy that, and then I'm going to bring it on down here. And hopefully we've seen from yesterday, all you need to do to switch the box plots is, first off, I'm going to make all of these say box instead of hist. And again, some extension work I would suggest you guys do is you can try to do these as side by sides. So you can do like the same exact thing and then say, okay, histogram here and then box plot here. Actually, we'll do that today because that's a good example there once we get through this box plot. So we go ahead and do our box plot here. Same setup, and then I want to specify, so I want to go ahead and say y equals. So the two arguments for this, if you want vertical box plots, you say y equals. If you want a horizontal box plot, you say x equals. So once you run that there, this would be like our outlier analysis. So you can see here that we're not actually going to really see any outliers here, which is great. Like all of our data, and it's sometimes easier to use a box plot over histograms. Histograms give you a good idea of shape, but box plots are really cool to see if like it's approximately normal. So the only one here that might not be like totally normal would be our green value here, that flipper length. We see that definite skew there. So we kind of see that like, okay, even though it looked a little better up here, it's definitely going to have some weird data values there due to that low column there. So this one would probably be one of the, not necessarily our best predictor, but it's also not like really, really bad. Like when we seen yesterday, we had some of those with a ton of outliers. So we don't really need to worry about removing it or doing any adjustments there. All right. So again, that idea of a side-by-side look, if you wanted to combine these together, what you could do is just, use these commands interchangeably. So maybe my first one's a box plot, and the next one I want to do a hist plot. So if I wanted to, look at this bill length side by side, I could plot the histogram and then right next to it, plot the box plot as well. That's one way you can kind of compare side by sides with variables. So again, that'd be something I would suggest to go ahead and try out. But for now, just to make sure we stay on track with the lesson, let's go ahead and do our categorical plot here. So I'm gonna go ahead and pull this in. So I'm gonna use the same couple commands here at the start. So I'm just gonna go ahead and copy and paste those. And then for this one, it's gonna be a little more narrow. So this one will have 3 when you look at those categorical variables. So I'm just gonna go ahead and make it a 6 here to make it a little smaller. With this one, we want those categoricals. We've seen yesterday, this is the one I had you kind of copy and paste in. So I'm gonna show you how to skeleton it now. So let's go ahead and do a count plot. So this is just gonna be, it's a nice way of saying bar graph. And then here we have to specify our data. Now with this one, I actually want to change the shape. Since I only have 3, I'm going to do 1 row with 3 columns. So our naming convention here is going to change a bit. So since we only have 1 row, we don't need to specify the row. We're just going to be picking off the columns there. And then that's going to kind of be our skeleton command for all 3 of these. So here are ones we're looking at species, island, and sex. And then our data set, they're all the same. We're doing DF penguins 1. And then the order here, so the first one is 0, 1, and then 2. So we're in the first, we have that 0 level row since we only have 1 of them. and then the 3 column variables there. So since we only have 1 here, we don't need to include that first argument. And before we do the rest, I just want you guys to see why we sometimes add in those extra things. So if I just run this, what is it not like here? List has no attribute bar. Why is it telling me that? Give me a second. Oh, I forgot to put axes here. There we go. So I need to specify that I'm referencing the axes objects there. There we go. So when we go ahead and run this, this is why I use those additional arguments at the bottom. So in this case, we probably don't need the rotation argument. I threw that in the notes if you want to. So what that's going to do is kind of rotate these around. So it'll give it more of like that like sideways look to read it. However, since I could see these, the Adelie, Chinstrap, and Gentoo, they're all kind of like, I can read them fine. I don't necessarily need to rotate those. And then the bottom here is just telling me which this is referencing. So this is my species, my island, and then the sex graph here. However, I really don't like how this like count is like overlaying on these. It kind of makes it ugly and hard to read, right? And I don't have a title, so I really can't look back and know it. So that's where these additional arguments at the bottom come in, where we use the subtitle to kind of get it on top. So I'm just going to say these are my categorical. Use that same y equals argument. And again, this will kind of get rid of any of that extra overlappy white space. And then the argument plt.show, all that does is it gets rid of this. So like you'll see that in a lot of tutorials not explained well. Like the only purpose of this line is so that this doesn't show up. So now we have it more spread out, right? We don't have that weird overlap in between these, so it's a little more readable. So some things to consider when we're looking at our category of variables here, because what we want to do, we want to build ourselves a classification model. So we want to be able to say like, okay, I need to create a good data set here so that when I'm training it, it's not biased in one way or the other. So one way we like kind of inadvertently induce bias into our model is we have really unequal groupings. And that's the trouble when you're building a kind of a training data set, is figuring out exactly, I guess you could say how well our data is going to look there in terms of like, what's the split? Like how many examples of each do I have? So for me here, the male-female thing isn't of concern. It looks like there's a couple more males than females. And you could do a dot value counts if you want the specifics, but like that's not a huge concern to me. When I'm looking over here, like the island, it seems like they're mostly from the Bisco Island, Dream, whereas Torgerson is pretty low. So if I was going to use this, I'd want to make sure I don't use all of this data. So basically we want to make sure that our examples for our training model are roughly equal, meaning it's not going to be biased here. So for example, if I used all of this data in the model, it'd be really biased towards these two over predicting this one, just because there wouldn't be many examples there. Same thing over here. If I looked at the species, if I used all of the data, like Adelie and Gentoo would have a lot more examples in there. So I'd see some unintentional bias there towards the chin strap being probably my worst prediction level. So in this case, what we're going to do here is we're going to do a little bit of prep work just to kind of make our data more equally distributed so that when we're building this model, it doesn't have that, kind of preference or bias towards one thing just because of how big it is. So I'm going to go ahead and type in what I just said here. I'm sharing that over in the chat just as comments so that you could see over in the shared notebook as well as here. This is kind of just a summary of what I said out loud there. So because we have these different kinds of columns, we want to do a little bit of cleaning. So we're going to remove what we don't need. So I liked what someone said at the start, the idea of predicting the species here. So where are we at? That was way back at the beginning when someone said we're going to look for species. So I like that. We can go for that. So we're going to go ahead and get rid of a couple of these things here. So maybe I'm not worried about the island. I'm saying, you know what? I really don't know if the island's going to make a huge difference. So I'm going to remove that for now. So here's a way to drop columns. So dropping a column, making a new data frame. So the idea of version control here, we're going to go ahead and make this penguins 2. So again, the idea of that numeric number at the end for my data frames, it's a clear logical order for me which data frame I'm on. So I know that, you know, penguins 1 came first and just penguins by itself, or you could say df penguins 0, whatever you want to do there. But this is kind of helping me build out like, okay, like here's how I know which data frame I'm working with. So I'm gonna say it's equal to df penguins 1. And then I'm gonna go ahead and drop, and I want to say what columns I want to drop. So I'm just gonna get rid of island, and then I'm gonna specify the axis of 0. So what that's doing is, just like we seen yesterday, we have to use the idea of, you know, including dummy variables in there of, you know, the 0 and 1s. Since I don't want to overcomplicate my data, I don't want to have any more of those dummy variables than I need. I'm going to say, okay, you know what? Let's try this model without island. Maybe I don't really need that to make a good prediction here about species. And then if I want to see how many of each I have now, so df penguins, like we talked about earlier, using a value counts argument, is we can go ahead and just say the species column and then value counts. For here, we're gonna want to use axis equals 0. So if I look at this now, so if I go and check out df penguins 2, so by saying axis equals 0, it just means remove the whole column itself. If we said axis equals 1, that's going to pull a row there. That's another one. That's a weird argument to get used to. So that's like when my notes there, I have the idea of dropping a column, making a new data frame. So whenever you want to drop a column, you want to specify that argument there. That's a lot of times we're getting new to coding. It's like that axis argument. You'll get errors sometimes if you do that. So just getting used to doing that as well, and always checking your work. So axis 0 just refers to the column. So it's saying to drop it based on the column as opposed to the row. So our value counts here, I could see if I'm looking. So here's my data frame. Here's what it looks like. It's just what we wanted. We just stripped out that island column. And then here, when I did this value counts argument, I'm just saying how much is each. So I looked at my graph and I'm like, okay, like there's definitely a lot less chin strap than the other two, but how many less? So here I can go ahead and say, all right, the chin strap only has 68. These others have much more. So when I kind of build out the new data set here, what I want to do is I'm going to make sure that they're all equal, because that's a great way if they're, I mean, again, and if you had a perfect data set, they'd all be equal. Sometimes if you have a good data set and they're close, like if I looked up here, like if this was maybe like if this orange bar was somewhere closer, I could say, you know what, let's just use it. It's not that bad. But since I'm seeing like these numbers, I mean, there's like, you know, more than double the chin strap for each of these. That's going to be kind of concern to me. So I'm going to go ahead and clean up this data a bit. So to do that, I'm going to make a couple new little data frames here from my sample. So I'm just going to call one the Adelie penguin. So that's the Adelie here. Looking at my species, I just named it that. And I'm going to say if equal to, oh, it should be df penguins 2, by the way. Same counts, just different ones. So there we go, df penguins 2. So I'm going to say this is equal to df penguins 2. df penguins 2. So what I'm looking to do here is just specify what rows I want. So I'm going to say that the species, and we think about that equals equals or exactly equal to or congruent to. So the thing that I wanted to say in there is it, yep, it's capitalized. So I'm going to say ADELI. So that word there, the Adelie or Adelie, not quite sure how to say it. That's going to be the ones I want. And what I'm going to do here is I'm going to say, give me a sample. So this is a cool little thing here from Pandas, the dot sample idea. And then you can just specify the number you want. So since I have 68 chin strap here, I want to take a sample of that. So what that's going to do is it's going to give me a random sample of 68 rows. So I'm not inducing any personal preference into here. I'm just going to go ahead and say, give me a sample of those. And then I'm going to go ahead and copy and paste this and do the exact same thing here for Gen 2. So this other one here. So coming from the same data frame, but I'm just going to change the species up here to that Gen 2. So what that's doing is this dot sample argument with a number. You can also use different things. So you could use like proportions if you want it. So maybe if you want 1/4 of the data, half the data, whatever it may be. However, when you can specify a number, it just makes it easier to get that random sampling there, so that again, like the test or our sample group here, it's not, we can't induce any form of bias, like we're just picking a random group here. So one thing we're going to do here is when we run this command, so this is where we're going to see some differences here between my data and your data, is every time you run this sample command, it gives you a different 10. So by using this method, we want to actually put together a new data frame here. So I don't want to rely on these two any longer than I have to. So what I'm going to do is I'm going to go ahead and create a new data frame here. So what we're going to do is I'm going to make a new data frame here. So since I'm using idea of version control, right, I'm going to call it df penguins 3. So this is going to be the one where we can put everything together. So when you combine data, there's two big ways to do it. There's concatenation and there's merging. Merging is if like I had two different databases and they had like an identifier column. So maybe I have my client's sales in one database, and then I have my client's ordering information in another. And I want it to make just one big spreadsheet or one database. Maybe I would merge those on the client ID column, right? So this unique identifier variable. Concatenation refers to when we want to go ahead and take things with the exact same headers or the exact same columns. So here we have 3 data frames that are exactly alike. Oh, we have 2. So we actually need to make our last one too. So let's go ahead and make the chin strap one. And this one, we can just kind of get rid of this part, the dot sample, because there is only 68. So I forgot to make that chin strap. Let's go ahead and make that as well. Now I'll go ahead and throw this over in the copy paster in a second here. So the reason why for chin strap, I don't need to specify the samples because we know there's only 68 of them. So there's no point. You could put this, it's not going to make a difference. But since we know that there's 68, we don't need to worry about that. So the concat here, we're going to say pd.concat. And then here, since we're using data frames, we're going to go ahead and put our brackets. And I'm just going to use those names. The order you combine them in isn't going to matter. So I'm just going to go in the top to bottom order here I wrote. And then this is another one here where we want to specify the axis. So I'll type out these notes in a second here of what this is doing. So what this is doing is it's stacking them vertically. So I'm going to go ahead and kind of show you here the error. If I here say axis 1, that's a horizontal. And then if I look at it there with that horizontal stacking, it just gets put side by side. So if you're noticing, this induces a very large amount of nans because it's trying to like just match on this whole column here. So it gives me a ton of columns with a bunch of empty, kind of not really usable data, because here it's basing it on the row index. So if you do a horizontal, so a side by side, it's going to be basing it on the row index. Whereas if I do the vertical, we can see this looks how we want it to, right? It's those same columns there. And again, it's just kind of listing them in order. So I know that the columns are in the same order and we're good there. So that's kind of the example there of the axis argument. Okay, awesome. Glad we're getting the axis thing. That was one of those things we can, I could say that was very challenging at first, kind of get when to use what. So with this step in the data is that, can we say we're normalizing it? So what I'd say here, the best way to describe what we're doing so far is we're making it identically distributed. So what that means is that now we have the same amount of each set of data. So if I go ahead and check out just a value counts here, is if I want to do value counts. So if I'm looking at my species argument now, oh, what did I, there we go. So the idea of identically distributed, so it's got the equal representation of each group. So this is now an equally representative group. So normalizing typically responds to or implies that we're kind of making all the data the same. So If I wanted to normalize data, it's basically putting different metrics on the same thing. So let's say I was comparing things like height and weight. So if we think about height, depending on where you are on the globe, you might be measuring in centimeters or you might be measuring in inches. So that would be our height variable. In weight, maybe we're measuring in pounds. So if I wanted to say, hey, which is more likely? So this would be a good thought question of when we want to worry about normalizing data. So which is more unlikely? Being over 6 feet tall or weighing over 200 pounds? So when we think about something like that, which is likely, so we're inducing probability into it, this is where the idea of normalization comes in here. So what I would want to do, since I'm comparing things with different measures, we would normalize that data so that I could then compare it. So if you have normalized data, it basically gives you a universal scale. So normalizing data. So that's if we're kind of looking for likelihood, or we're saying like, so for this part where we've kind of specified the number of occurrences there, we're just trying to make it more of a balanced distribution. So we get rid of any bias in that sample. All right, so what I want you to try to do next, and we'll do that 2-minute where you kind of use your example code and you try to get to it on your own, and then we'll talk through it here. So what I want you to do is we're gonna go ahead and make a new one. I'm trying to see what I want you to do next. Okay, so what I want you to do is to try and I want you to try and get a dummy variable for sex. So if we look at our current data frame here, we have that sex column still in here. What I want you to do is to try to binarize that, or to get the dummy variable there. So to kind of get you started here, if I were going to name this using our version control here, maybe it's penguins 4 because we just did 3. And you'd be looking for the command of pd.get dummies. You want to specify your data. And then you want to go ahead and specify your columns here. So think about what we're putting in there for each. And there's other ways to do this. You can like kind of do it on a specific axis and then drop some things and then add in some things. But this is kind of the most preferable and shorthand way to do it. Awesome. Yep. That get dummies function. So where that comes from is that was our PD imports. We said import pandas is PD. So dummies is the way of getting that. So here for our data, we'd be wanting df penguins 3. And then the column we're concerned about is the sex column. So if I check out what that looks like after executing this, we can see what we have here. And it gives us that binarized variable. So it dropped the sex column, which was occurring on the end anyway, and it gives me sex underscore female, sex male, and the 0 means it is not true. The 1 means it's true. So I could see here the first 2 were male. And if I go ahead and just make this for comparison's sake, 3 by 3, or pulling 3 rows out there, I could see the female is coded correctly as well. So if we kind of see through that there, what we're doing is getting those dummy variables so we can include this in our modeling here of the 0, 1 output there. So again, we can do this with more, and again, it's really all going to be based on how large a data set is. So if you have like, say, 10,000 values, maybe you want to binarize a bunch of things. Maybe I want to keep the island argument in there. But since we only had, a little over 300, I try to keep, because the more outputs here of these 0s and 1s, the more confusing your model can be. So I would say kind of only look at them one at a time as a rule of thumb. All right, bias or error or residual, are they all the same thing? So this is a great kind of thing where the stats vocab comes in. So if we want to think about bias, what that's going to be is bias is kind of like an unintentional preference for one. So the way we think about bias here is unintentional preference for one or more outcomes in a given data set. So for example, we could have much more male than female data. So when I think about bias in a data set, it's just that I'm happening to train one thing much better. So if I only have mostly male data, it's going to be kind of hard to make good conclusions about female data. So what you want to think about when you're looking to avoid bias in a data set is that next bit there I put in the chat. So representative data samples. So when I work with stats students, the first thing I always say is when you're looking at good data or if you want to refute something. So if you see an article in the news or you want to see something that you want to check on the study and try to refute it, is looking at how representative their data sample is. So a lot of statistics we see are always cited of like in a sample of 1,000 people, it's like, well, who are the 1,000 people? Because if they're not representative of a larger, like for example, in elections, voting, we always see these predictions made. And it's like, if you don't have a great sample, it's going to be really hard to actually make a conclusion about a larger group here. So for example here, representative means all those subgroup proportions are approximately representative of the population. So in this case here, if we wanted to really dig through and make the world's most perfect sample, we'd actually want to narrow it down by everything. We want to look at species, we want to look at island, and we'd want to look at sex. Now, the cool part about stats is maybe in this case, I don't have enough data to be that particular where I'm going to look at every possible subgroup and make them roughly equally proportionate. So that's just something I would state in my conclusion. So if I was typing up a white paper style report on this, what you want to do is you kind of formalize your comments throughout the code. So it's okay, hey, we removed the island variable because we're not trying to factor that into our conclusion. Here's why we remove these blanks, because we wanted to get rid of the nans to avoid any kind of issues with that data. We still had enough. We removed less than 5% of the data. So if you think about going from the practical project to the kind of more academic level white paper, it's just about kind of justifying your conclusions along the way. Those other ones, so residuals and error. So these kind of vary depending on what you're kind of looking at. So the typical way we think about residuals and error measures are the difference. So these are going to be the difference, a predicted and an actual value. So when we think about a general plot, right? So if we think about a scatter plot and we're kind of looking at the predicted values there. So we can kind of see it going through the middle where we have that regression line that we're kind of looking like, okay, this is my prediction line. The distance between a point on top, so the distance between here, between my finger and my hand, so that distance is represented by the residual or the error, right? So it's how far it is. So if we think back to when we did the error max predictions there, we could see that error or that residual there was the distance between the prediction and the actual. All right. So let's go ahead now. We have our data frame here. So this is going to be like our final data frame, this DF Penguins 4. So I'm going to go ahead now and suggest something else. So if we want to go ahead and move on, we're going to go ahead and do our training and testing. So we created a train data frame and we created a test data frame. So to do this, kind of our general way of doing this is using this nice import train test split where it gets random samples from it. So first I tell it where to look for the data. I'm going to say look at DF Penguins 4. And then we're going to play around a little bit here with some different test sizes. So when you're doing this, like we talked about yesterday, the standard kind of rule of thumb here is an 80-20. However, if we want to look at the shape of this thing, I don't have like a ton of data, right? I only have 204 samples. So maybe I want to make my testing and training sizes a little different. So this is where we can kind of play around with the test size based on how much data you have. So in a perfect world, your training data is going to be massive. So when we think about these really cool, AI algorithms where we think, oh, Google Photos can recognize me from like any angle possible. How does it do that? It's the idea that it's taking in a ton of example data. So, if you store anything in Google Photos, like it's probably used in some AI model to help recognize people versus cats or dogs, whatever it may be. So when you're working with limited data here, you can kind of play around with these different sizes. So for this, let's start off with like a 0.3 test size. So it's keeping 30% of my data as a holdout here for testing. And then if we want to use that random state argument again, this just induces consistency. So I'm gonna go ahead and pick the number 1 there. All right, let's go ahead and build our testing data. So I'm going to update the shared code real quick here. So if you give me a second. So what we're looking to predict here is the species. So I'm updating that shared code now, and then I'll show it on screen in a second here. So that is what we're looking at there for our, and it's also in the shared file as well. So we're using these two data frames up here, the train and test df. I'm splitting into my X train test and then my Y train test. So here we want to drop the column species because it wouldn't make sense to tell it what it's using. And then here, so again, the features. So when we name those things, features are the variables being used to train. A target is what we are predicting. So I'm gonna go ahead and run that. Now, what we're going to start with here. So yesterday we went all the way to, evaluating different models together. What I want you to kind of see here is what it would look like if you're just building out one model. So for the type of report we're going to use here, we're going to use what's called a confusion matrix and get a visualization. So to do that, it's specific to this visualization. We actually have to do a little more work here. So we're going to do a couple steps in what's called binarizing. So I'm going to type this out first, and then we'll go ahead and explain it together. Actually, for the sake of time, I want to make sure we can get through all of our examples today. So I'm going to go ahead and do a nice little copy and paste here for you guys, and then get that for you. So give me a second here while I update some things, then I'll share over the code as well. So what this is going to do is it's going to go ahead and create just like a tag, almost like a little bit of a dictionary for me here. So the reason why we have to do this is because for the type of visualization we're going to make, they only work if you kind of use these indexed tags here. So if you want to look at what this is doing, is factorizing. So it just kind of creates a numerical reference for something. So I'm looking at the species, so our three different types, and I'm just factorizing as 0, 1, and 2. And then I'm creating a dictionary here just to kind of map back to. So I put that in the shared file as well. So, and you can go and say this is specific for this work. So it's specific for what we're doing here. So to get this nice little classification report, this is one of those steps that you actually need. So I'm gonna go ahead and type that in here as well. So this isn't something we've always seen done. It's going to kind of be more specific again to this thing I want to teach you how to build. All right, so let's go ahead and build a model now. So maybe we want to go ahead and work with just naive Bayes. So multinomial naive Bayes. What this is going to do is it's going to show us how to kind of look at just one at a time. Because so far we've been looking at a ton at a time. I want to make sure we have a good model for that as well. So here I'm going to say my model, and I'm just going to do an underscore NB for naive Bayes. And it's equal to multinomial NB. So I'm creating a model and I'm defining it. That's one of those imports we had earlier. And then I'm going to go ahead and say model NB, and we're going to say dot fit. And I'm going to use my training data. So X train and Y train. Output there just tells me the model that was fit on it, which is fine. So it's just saying, hey, we fit this model to the data. So that line of code there fits the model. So it says use this model on my training data. And then what we want to go here is build our predictions or output. So to do that, I'm going to say my Y prediction for naive Bayes. And that variable naming here, you could call this like literally anything. This is just kind of standard Pythonic like practice for when you're building models, so that if you're comparing it to other code or you're sharing it with someone, they will have a good idea what you're doing there. And then we're going to do our predictions based on our X test data. So it's applying my model to my test data to get those predictions. So what I'm comparing now is these predictions. That's my predicted values, and then here's my test values. So it's saying, okay, like how similar are these? And then let's go ahead here and we're going to build our confusion matrix. And then I'll update all this in the shared file in a second here. So I'm going to build out a confusion matrix. And to do that, I'm going to call on that import we had way back at the beginning of today. It's a confusion matrix. And I'm going to say my Y test and convert it to my Y predicted there. Now, if I print this just as it is, it's kind of ugly, right? That doesn't look totally like, oh, this is really user-friendly to interpret. Basically, the middle is the good stuff, right? So the middle ones are good, correct predictions. However, we can definitely make this a bit more visually appealing. So I'm gonna go ahead and update the shared file real quick here with what we've done. And then I will show you how to create a better kind of plot there to see a little more. So this kind of falls into the styling aspect of coding. This is really just not an overall nice thing to read. Again, if it's just you, it's like, oh cool, like I got these right. And then my errors are the 3, 6, and 1, and then 0, 1, 0 here. However, if I'm presenting this, I want to make it look a little bit nicer. So first thing we're going to do here is we're going to make a combined heat map and confusion matrix with better styling. Okay, so first thing we do here is we're going to say set our color codes equal true. And again, this is one of those commands we're not actually seeing any difference in here. However, when you sometimes use different notebooks, like for example, if you're using Google Colab ever, this is something that's super useful, because otherwise, like if you have like the dark mode on, so like how I share the files over, if you have this dark mode and you don't say that, it's really, really annoying, and it makes it look hard to read. And the same thing if you have like your browser set up different with like a filter on Jupiter. So that's one of those things. It doesn't actually change a whole lot unless you need it to, but it's also really not going to affect the way your code looks or runs. So I always say to put it in. Okay, so here we're going to use a heat map. So in this, the first thing we're going to do is we're going to reference the confusion matrix we want. So my confusion matrix, so it's just a data set here, an array. For a color map, and I'll show you some other ones here. Personally, greens I prefer, just because it kind of shows up very distinctively. Our anodes argument, so our annotation argument, we want to set to true. The line widths. So what this is going to do, we'll kind of play with this argument a bit here as well. But again, I want you to get the default one here. So this is saying like how much space there is between these different boxes. So when we plot a nice box around each of these numbers to make it look nicer, that's going to say how much space is in there. For readability in this, at this point after line widths, I have a comma and then I hit enter, just to kind of give it a little more, usefulness there. Our X tick labels, so where we're going to get the labels from. This is where we did that factorizing earlier. So back up here, this is just so we can get nice labels. So to do that, I'm going to say speech ID data frame. So that was the one I created there where I built that dictionary to reference. And there I want the species, and I want to say dot values. And then for my Y tick labels, it's actually going to be the same argument. So I'm going to go ahead and just do a copy and paste there. So this is one of those things. It's kind of getting a cool specific visualization here, which I'm going to go ahead and run, and then I'll copy and paste it over to the shared code file. So these line widths argument here, all this is doing is saying like, see that little tiny bit of white space in between those? If I don't have that, so if I just set it equal to 0, they're like right on top of each other, which again is totally a user preference type thing. I always like to just put that 0.5 just because it gives me a little bit of space between, so I can see a little bit of white space there. On the right side here, we have our color scale being shown. So I could see from 0 to 17.5 is that darkest green color. So my darkest value here, so all it did was take these numbers and make it in a much more presentable fashion heat map. There's a nice little resource there if you're looking at heat maps and different ways to change this. So instead of greens, maybe I want to use blues. It'll look like that. So again, it's kind of a color preference thing. So this is going on that same color palette we've used before. If you check out some of those examples too, you could actually use like really like kind of like customizable ones as well. Like there's a blue purple combination. There's different ones as well, where you can kind of see those other resources there. So that's one of those things, if you just kind of Google around, you could find some good examples with as well. That one's kind of a good one for me that I like to use. So typically I prefer blues or greens. Like there's some ones you could do like a red to green, or like kind of like more like Excel-y, like profit type stuff. But since I'm just looking at classification reports here, I usually pick blues or greens, just to kind of see how that's going to look. So what this represents here is going to be how we interpret this data, so how accurate it is. Now, good thing, all my darkest colors here are in the middle, so this means correct. So this means an addli was classified with an addli, or here, Gen 2 and Gen 2, so correct classifications. So if I'm looking for errors here, if I look at just my addli, we can kind of see how many we had there, so how many were misclassified. So again, darker numbers in the middle means you're doing pretty good. So in total, we only had a handful here that were incorrectly classified. Now, the other thing I want us to look at is a classification report. So this is another option here when you're evaluating a model. You can look at the whole classification report. So when I do these, I typically just do 2 print arguments. So this is just saying, hey, on the first line here, let's go ahead and give it a nice little title. And then I'm gonna go ahead and say print. I want my classification, a lot of spelling there, report. And I'm just gonna use that same argument there of y test, and then my predicted. And I'll share that over in a second here. So this is kind of a standard of evaluating how well a model did. So we can see here my addli had my most precision, and then chinstrap, and then Gen 2 is at the bottom. The support refers to how many examples I had. So in my train data, I had 24 examples here, 18 here, and then 20 here. So if you're looking at that article I shared in the chat, if you kind of read through this, this will give you another idea of how to interpret this report. So it kind of shows you here the different types of outcomes in a confusion matrix. And then those indicator variables there. So to not label positives into negatives, that gives us our precision. So to not say that this example is something else, recall, F1 score, and support. So if you kind of read through those, that'll give you more of an understanding of how to actually like read one of these. In general, you kind of look at your precision up here first and see how well it's doing. Like, okay, like all these are pretty good. And it gives you an idea of what you're classifying well versus others. So if I was going to make a marketable model here, maybe I would be looking at saying, hey, can I classify just addli penguins? So can I say addli or not addli? So maybe my new problem definition is going back up, and I'm going to change this. I'm going to, replace the words. It's either an addli penguin, or I'm going to rename these, combine them together and say not addli penguin. So if we're looking at how to interpret this, so if you're looking at precision, it's how accurate this is. So if I look at this vertical column here for addli, that means I got 15 right, and then here's the one I misclassified. So that's kind of where those are coming from. And then in our shared file here, just for the sake of time, I'm gonna go ahead and copy over some code for you and some comments as well. So these are kind of my notes in addition to that article, and I put these in that shared file here about how to interpret that as well. So those are my notes on kind of looking at that there. So if you're looking at that F1 score, 1.0 is great, 0.0 is terrible. So what they're saying there, and this one is kind of the big part here. Well, I am they. So looking at this, F1 scores are used for comparing models. So a higher F1 score is used to say it's a better model than something else. So what that means here is that an F1 score is kind of relative to comparison tool, as opposed to like saying, well, hey, my model is great because look at its F1 score. You want to use that. So if I built one model and I compared it to another, an F1 score is a good thing to compare by there. All right, so that was our example of doing one classification model. We want to go ahead and build out something larger here. So I'm gonna go ahead and start typing this out. So I'm gonna type for a bit, and then we'll talk through our code. Actually, you know what? This is one of those larger ones as well here. I think we've seen this before. So I'm gonna go ahead and just do a share for a larger thing of code here, and you'll see the notes in there as well. So I put that in our shared file, and that's what I'm bringing in now. So this is just going to be that same kind of block of code. And you're noticing I'm using this in a lot of different instances. This is probably one of the best things I can suggest that you use. Only because, again, we're going to see here, this is a great way of kind of just testing a bunch of different models together. And then this can be in combination, like we've seen before, if we do want to do a little bit of stacking within our model. This is kind of that baseline for it as well. So at level 1, level 0 are learner modules there. Now you'll notice I split this, so I don't have the visualization built in. So we can just kind of run this and see how it looks. So splitting our features targets. So features, what we're learning from. Target is what we're trying to predict. This is with logistic regression. This is just kind of a standard input here. For the sake of time today, if you're looking at the specific commands I'm using here with logistic regression, you can kind of look that up on sklearn, as we've seen before, to kind of see the different options there. And we've seen all these before. The setup here kind of similar. For today, like I said, if you're someone who reported having a little bit of challenge there with the CV level, maybe change it to 2 or to 3, just kind of seeing the different options there. I'm just going to run mine with 5 right now, just so we can kind of see it. And then here our scoring is going to be on accuracy, just because, again, we're doing classification. So it's running on my side now. And then let's just go ahead and take a look at this data frame that we got, so this CV data frame. So what it's referencing here, it's showing me each iteration here. So all 5 iterations, or if you used a smaller number, there would just be less here, and they always start with 0. And then the accuracy that it used. So if I'm looking just at this multinomial here, like we've seen, I have some in the 8s. I have one really good here at 9.3. For logistic regression, we've seen some really good success rates here, right? All above 9s, our k-neighbors, SVC, and our random forest. So let's see what these look like now if I kind of do that visualization piece. So again here, just for the sake of time, I'm sharing over that code in the shared file as well to get those box plots. So this is visualized, and I shared it over in our code as well here. You can kind of do the copy and paste there. Now, again, yours may look a little different. So your outputs here may be a little different than mine just because the way we sampled. So for mine, if I'm looking here, okay, it looks like I have a couple of models that are just not really keeping up with the others. Here I can see my k-neighbors has a higher level of standard deviation and variance because it's more spread out. My SVC kind of seemed to be the lowest performing. So I can say like, okay, well, this is pretty low here. Like that would be probably not the best model to use. These two look, this is a good comparison example here. So let's go ahead and just kind of visualize. I'm going to go ahead and just take out everything here except logistic and random forest classifier. And we're going to talk about how to define which of these might be a better model here. So I'm just going to go ahead and copy some code here. And I'm going to use just those 2 models. So I'm going to take out everything except logistic and my random forest here. So I'm just kind of copying that code, just so we have both examples there. So when we run these side by side, so again, if you're getting caught up there, we remove those other models. So we just specified, and you look in the shared file, you can kind of copy and paste this. I just want you to think about it. If you had to pick one of these, which one would it be and why? So for comparing these two, we really want to start thinking about what each of these sort of represents here. So in our logistic regression, we see we have more variance. So we have that higher level of standard deviation here if we're looking at these side by side. So I have my bottom and my top, with most of them falling right around here. So I could see 3 of those 5 dots are pretty much exactly the same. So if I go ahead and just check out that CVDF here, I could see most of mine are right around that 9.6 level. And I had those 2 that came out perfect with accuracy at 1.0. And if I'm looking over here, I could see that I have 3 right here with my accuracy being right around that same point. 1 real high, 1 a bit lower at 0.93. So if you come to a case here where the models are looking so similar, and with your cross validations, it kind of just like, logistic regression happened to have a high one, this one happened to have a low one. This is a point here when you have 2 very, very similar models. So let's go ahead and I'm gonna go ahead and bring over a comparison here. So if I wanna compare these 2, and I'm putting that in the code as well. And again, the reason I'm kind of doing the copy and paste feature here for you is just for the sake of time, so we can get through some good examples. If I'm comparing these 2, so what this did was just kind of gave us a summary here, just a group by to look at that comparison. I can see that these are really, really similar. And I think the only thing that's upping logistic regression here is the fact that on that 5th cross validation, it happened to get a higher score than random forest. So maybe I want to look at these again. So this would be an example. And again, depending on the machine you're running, this might be a very time consuming to run right now. But for the sake of our talk through and our understanding, I'm going to go ahead and run it here. I'm going to turn my cross validations up. So I'm going to turn them way up in here. So instead of 5, I'm just going to double it to 10. And again, depending on the machine you're on, you may or may not want to do this because it might take a while, but I'd rather you see the example on my side. So this is something I do when I kind of see that like, hey, these models are looking really, really similar here, and I want to see which one's best. So if I ran that with 10, or maybe just for here, let's do something really large. Okay, I'm gonna run it with like 30, just to kind of see how different these models are. So running with a very huge number of cross validations here, just so we can get a better visualization and kind of get more understanding of those. So you can see I now have a gigantic one, right? For my cross val comparison, go and get rid of that. And if I visualize this, we're seeing here the disparity in these models is pretty similar. They're either hitting way down there at 0.8. So the more cross validations, it's likely you're going to get more, I guess you could say, bad ones coming in at the bottom as well. And we can kind of see it spacing up here at the top. So now if I rerun this again, we're noticing that these 2 models are getting closer and closer together. So I can see that 0.98 and that 0.97333. So we're kind of seeing that side by side there of which one is getting better. Honestly, at this point, these are pretty much totally comparable models. When they're this close together, accuracy is not really going to mean like a vast difference, I guess you could say. It's going to kind of tell you like, hey, look, like these are pretty much the exact same. Because as I cranked up those cross validations, it looks like I'm getting slightly better values with logistic, but not something that would make a huge difference. So that's something to consider there when you're working on these types of models, is ways that you can improve upon that. So that ways you can just knock this down and figure out which one you may want. So you might want to go back and test different sides. So with this sample, we said, okay, logistic regression and my random forest were the best 2. I'm going to scroll all the way back up here. And let's see if I change my sample size. So this is something I suggested playing around with yourself. So here, maybe if I make my test size, what if I made it 0.2? So what I'm going to do on my side here is just rerun all this code. So I'm just holding the shift key and pressing enter a bunch. We're going to see how that's going to change things up. So by making that test size a little smaller, we're seeing some definitive increases here. So all I did was kick an extra 10% into my training model. And we're seeing some very different results here. So we're seeing now with that increase in the training here, logistic regression and random forest have really amped up even higher. So they're even more comparable. All of these models actually got a bit better too. So my multinomial here, naive Bayes, actually got better as well. So that lower part kind of shot up. And then now I'm going to go ahead and rerun this here. Let's just make it like 20 cross validations there. So we can kind of see how that's going to look in our plot here. So when I increased the sample size there for my training, we can now see that these are almost perfect models. So just by increasing that sample size a little bit, we then got to pretty much perfect models here. So either one of these would work great with this. To see the other side of it, So if I change how big that training sample is, so let's say I went back up to here and I made my test size something like 0.5. So I'm only using half my data for training, half for testing. We can kind of see how that's going to change things up. So here, when I lower that, so when I lowered that threshold of how much training data I have, that's where we introduce some more variability here into the logistic and the random forest. So I'm going to this to execute. So when I lowered that, we can kind of see here, this is where I'm getting these plots at down here of much lower values. So even though the accuracy might be high, I'm seeing that, okay, like on certain instances of these cross validations, I did do low. So what you're going to want to see here is, again, that's where kind of that rule of that split comes in. When we go back up here, the more you can put into your training, so a lower test size there at that 0.2, that kind of gave us the optimal outcome there. So that 80-20 split there gave us pretty much the best modeling we were going to find with that output there for our box plots. And again, that very good accuracy there. Perfect. So yeah, let's go ahead and see what that looks like. So if I increase my test size, what that's doing is it's giving me less train data. So when we specify the test size argument here, let me go ahead and put some notes in here for you on that. So it's this idea here that our test size plus our train size is equal to just 1. So if I go ahead and crank that test size up, so let's say I make it like 0.7. What that's saying is I'm only using 30% of my data to train. So if I go ahead and rerun this, we can kind of see the increase here. So we'll see a lot more variance within that. So typically the larger your test size is going to be is the more kind of anomalous or outlier values you'll see in there. So the extensions here that we could think about doing would be, and then this homework assignment is shared with you as well, is what you guys want to work on here to kind of build this out is classifying by something else. So we did species, maybe try to classify by island, or you could maybe use sex there. So you could try either of those. So what this is going to change in your code is you've already done the exploration, you've already worked through it, you've kind of seen the different ways to get to it. So what this is going to change up here, the easier one of these two would be by sex. I will tell you that. You'll have better results by sex than by island. If you're looking to try to really build a crazy cool model where it's going to involve some extra work that we may or may not have covered, then I would say island because it's going to be a bit more challenging. But if you want to classify by sex, that one you don't have to do as much cleaning. So what's going to be in here? The steps are going to vary depending on what you're looking to do here. So the visualizations are the same. The model development is going to be similar here for this classification. The thing that might change here is which of these you're doing. So for example, like sex, like I said, will be the easier one. It'll involve less, I guess you could say, work. Only because, like, for example, if I go way back to the top here on our categorical distribution here, sex is pretty much equal between the two. So this male-female comparison, if you're looking to go through that, what I would suggest is checking out the male-female because since it's pretty much already equal, you don't need to do as much cleaning or creating different samples. You can kind of go right into the modeling. And then something else I'd suggest here is if you guys want to try to add in, you could try to use some of the stacking techniques that we've learned. So you could try to use stacking. So if you want to look at trying to include stacking when you're doing this work, that would be another cool thing too. So maybe you can kind of see, okay, for male, female, what can we stack to maybe get some better results here as well. And again, if you're doing the island argument here, this one will involve a little more cleaning because we can see similar to our species, there's a noted disparity here between the Torgerson and the other two islands there. So maybe you want to define your model is just looking at the Bisco Island and seeing how well you can do that. So that's the cool part about when you're doing exploratory data analysis is there's no real forced way to do it. So maybe I'm saying that your project goal is to look at, okay, pick one of these and say I'm running a business and I want to, be able to market things about these different penguins here. I would maybe be really excited with a really good model for Bisco and then its own very good model for Dream. So maybe you're just specifying the penguins by that and you're saying, hey, if I know the island that they're from, I can predict if they're male or female, or I can predict if they're a different species.